and the others in Berkeley. And he's going to talk about superintegral systems and representation theory.
Change that.
Floor is yours, Nicolai.
Actually, yes, I didn't change the title. It's just it's a mistake. I was thinking about representation theory, and it's the second title. Let's put it this way. So here's the plan. So first I will talk about classical superintegrability, and then quantum integrability, and actually it will be also superintegrability. The simplest example, I think everybody knows this, but just maybe not everybody. So the simplest example of a quantum superintegrable system is the hydrogen atom, the model of the hydrogen atom. And then after this introduction, I will focus on quantum spin Calogero-Moser chains, and then we will see that somehow these integrable quantum systems are closely related to well-known subject to two-dimensional Yang-Mills theory. So we'll see how it happens, and then I will discuss some sort of other directions. So this project is part of an ongoing project with Jasper Stockman. I think I mentioned it here. So, and also, well, since Misha already said a few words about how he met John, so I should also continue this tradition. So I think, John, I don't know, you can correct me, but I think we first met 32 years ago.
Sounds
in 1990 at one of the conferences.
Sounds reasonable.
So, and then most remarkable meeting was in Charles de Gaulle Airport.
Yes, I remember that.
I don't remember where I was flying to, and I don't remember where John was flying to, but we just met there waiting for the plane. So, okay, so now let's start.
Sure.
So first, I will introduce the notion of classical superintegrability, but of course I'm talking in Montreal, so I should have put here instead of ... the name of Paul Winternitz. So this is the notion that refines Liouville integrability, and geometrically it's the following. We have instead of Lagrangian projection that characterizes Liouville integrable systems, we have two projections. First, both projections P1 and P2 are Poisson projections. So first projection is to a Poisson manifold of dimension 2n minus k, and the second projection is to the Poisson manifold of dimension k. So the base has a trivial Poisson structure, just as in the Liouville case. The intermediate Poisson structure is such that fibers, generic fibers of P2 are symplectic manifolds, and connected components of generic fibers are symplectic leaves. So this notion goes back, actually it goes back to the 18th century. The very first classical superintegrable system is Kepler system. So it was studied by, so these extra integrals in the Kepler system were found by Jacob Hermann, who was a student of Jacob Bernoulli. And according to Jacob Bernoulli, he was the best student of Bernoulli. And then there is a long story about these extra integrals. So now they called Laplace Runge length vectors, but they were geometrically discovered by this fellow who was a cousin of the mother of Euler. And then later he worked in St. Petersburg in the Academy of Science, which was, anyway, so this is a long historical, long history here. So I will just leave it here. So algebraically, this means the following: if we use the pullbacks, then we have a Poisson algebra with the trivial center, the algebra functions on our symplectic manifold, the intermediate Poisson algebra functions on the intermediate Poisson manifold, and Poisson commutative subalgebra of functions on the base. So this is what we have from this geometric definition. So obviously the rank of this algebra is 2n, this one 2n minus k, this one k. By the rank, I mean the maximal number of algebraically independent elements. So algebraically, this system is superintegrable. And now by this system, I mean the embeddings of Poisson algebras is superintegrable if the centralizer, if the Poisson centralizer has maximal possible rank. In our case, it's 2n minus k. So it's the function on 2n minus k dimensional Poisson manifold. So more generically, algebraically, if you have a Poisson algebra with trivial center, that's our algebra functions on the symplectic manifold. If we have a Poisson commutative subalgebra, then we always have this system of embeddings. The centralizer of this Poisson commutative subalgebra in A will be bigger or equal than I, and it will be subalgebra in A. So the definition is that this pair Poisson commutative subalgebra in A is a superintegrable system if the centralizer of this Poisson commutative subalgebra in A has maximal rank. Maximal possible rank in this situation is the one that is complementary to the rank of I in A. And then, so this is a generalization of the Liouville theorem. So the Liouville case. So first of all, non-integrable case. It's a typical case. Choose any Poisson commutative subalgebra sequence generated by one element in your favorite Poisson algebra, and its centralizer typically will be just the algebra itself. You don't have to expect any extra elements Poisson commuting with I. So non-integrable case is typical. And that's the case when the centralizer of I in A is equal to I. So then the other case is Liouville. This case, rank of I is equal to rank of A over 2. And in this case, the centralizer is equal to I, but I has maximal possible size for Poisson commutative subalgebra. So the theorem that I'm going to explain now, it's a version of the Liouville theorem in this setup, in the setup of superintegrable systems. So first statement is that if you choose any Hamiltonian from this family of commuting Hamiltonians and any point in M, then flow lines of this Hamiltonian passing through X, they will be in the fiber of P1 that contains X. So in other words, flow lines will be always in the fibers of P1. They will not go from fiber to fiber. So now that's the first statement. That's just the same as in the Liouville case. Flow lines, they go along the level surfaces of integrals. So now let's choose a maximal independent set in I. Their flow lines generate affine coordinates on fibers of P1. That's a theorem. So affine coordinates, meaning that coordinate transformations are linear transformations with the translations. So changing this maximum independent set is like changing coordinates on the base B. So when you change coordinates, you get different affine coordinate system. So as a result, you have the this pair. These are the action. So this is the action. These are the angle coordinates. Now each fiber of P1 is isomorphic to the product of some copy of Rn and a torus. That's just the same as in the Liouville theorem. It's just purely topological statement coming from the toric action of the of this maximal of this Poisson commutative subalgebra. And then the most important thing is that now in the Liouville case there is only this term. So action angle variables, they give Darboux coordinates for our Poisson, for our symplectic manifold M. So now it's not the case. So they give partial Darboux coordinates. So now we have these projections, and here the fibers are connected components of fibers are symplectic leaves. So each symplectic leaf has its own symplectic structure, and that's exactly this missing piece omega k. So the dimension of fibers here is 2 generic fibers is 2n minus 2k, and so this is this kind of strange description of the symplectic form. We can say that action angle variables in this case are partial Darboux coordinates. Okay, so so now if we fix a Hamiltonian in our Poisson commutative subalgebra, then just as in the Liouville case, the flow lines of the corresponding Hamiltonian vector field are linear in angle coordinates, and so the evolution is in these coordinates is given by this formula. So all we have to do if we want to solve these dynamics is to have a way how to describe action angle variables. And of course, this is the technicality where the devil is sitting. So it's difficult to do this. But that's the main feature of these integrable systems that can be integrated using representation theory, using Lie algebra. In all these systems, there is an algebraic way to construct action angle variables, and so you don't have to solve differential equations. Analysis is replaced by algebra and geometry. So if k equals n, so this in these projections, that's the case of the Liouville theorem, and maybe I can try a trick. So here's an example of, say, let's consider 4-dimensional symplectic manifold, and suppose we have an integrable system, Liouville integrable system. So all we know is that if we have a compact level surface of Poisson commuting Hamiltonians, then it's a 2-dimensional torus. We don't know how the trajectories go around this torus, whether they are periodic or whether they are covering this torus completely. In the superintegrables case, they are periodic, something like this. So you can say that if the system is Liouville integrable and superintegrable, then superintegrable system is refining Liouville integrability. So in this dynamical sense, superintegrability is a stronger notion than Liouville integrability. And last remark is, so our phase space is 2n dimensional, the base is k dimensional. So locally, and we can represent M2n as some kind of phase space, reduced phase space, which is 2k dimensional and 2n minus 2k dimensional piece. So here we have dynamics and action angle variables, and here we have nothing. All these coordinates, they don't change locally in the dynamics. So there are super integrable systems that split globally. In this case, you can forget about this piece. But typically, you cannot do it. Typically, sort of they all intertwined, and only locally you can represent the dynamics in this way. Okay, so I think I said everything about classical case. So now let's move rapidly to the quantum case. So by quantum case, I mean always that we have some family of algebras that quantize the classical Hamiltonian dynamics, classical Hamiltonian system. So here is the most obvious definition of what we should call superintegrable quantization of a classical superintegrable system. Is suppose that we have this classical superintegrable system, then its quantization is a deformation of the commutative deformation of this Poisson commutative algebra I, such that so now it's a subalgebra inside this quantum algebra, such that its centralizer is a deformation quantization of this intermediate Poisson algebra and is maximal in our quantized algebra of functions. So here is some kind of crude idea of what maximal should be. So in this subalgebra Z, we can look for maximal commutative subalgebra. And by maximality, I mean the rank of this maximal commutative subalgebra should be maximal. So yeah, so that's the notion of maximality. So this commutative subalgebra is the subalgebra of quantum commuting Hamiltonians, and the subalgebra, its centralizer is the algebra of quantum integrals of motion, since all elements from there are centralizing quantum commuting Hamiltonians, they are all preserved by the evolution, and this is why these are quantum integrals. So the idea of classical quantum superintegrability is that you have this distinct subalgebra of Poisson commuting or commuting Hamiltonians, but then in addition you have a huge subalgebra of elements that are preserved by these evolutions. So huge subalgebra of quantum integrals of motions, and by huge I mean maximal possible. Okay, so suppose we have a quantum superintegrable system and a representation of this big algebra. So then let's look for an eigenspace of this commutative subalgebra I that we have here. And here's the definition. This pair algebra A and with the commutative subalgebra I that has maximal centralizer is called simple superintegrable system. If each of these spectral subspaces is an irreducible module over the centralizer. So this notion of simplicity is not very important, but it is important in some sense. It's like irreducibility. So this is a quantum version of the property that the fibers of the second projection are connected. In other words, fibers of the second projection are symplectic leaves, not just connected components are symplectic leaves. So the next notion after this simplicity would be semi-simplicity, when this is a direct sum of finitely many irreducible representations and so on. Okay, so we have the notion of quantum superintegrable system. We have the notion of simple quantum superintegrable system. And now let's look at the kind of historically first quantum superintegrable system. That's the Bohr model of the hydrogen atom. So in this case, the algebra A is the algebra of differential operators depending on H. So momentum is represented by minus IH ddqj as usual. So we have the Hamiltonian of the hydrogen atom, this Laplacian minus Coulomb interaction. The subalgebra I is the algebra of polynomials in H. And then the next theorem can be attributed to Fock and Pauli. Basically, they did everything that's necessary. So the statement is that the centralizer of this Hamiltonian, in other words, complete collection of symmetries of this Hamiltonian, quantum Hamiltonian, is generated by the angular momentum. This is obvious because the system is spherically invariant. By the Runge length vector, as Pauli called it. So that actually was discovered by Lenz. Runge gave an exposition. He had a very nice textbook where he explained the results of Gibbs, who used vector analysis to derive these extra integrals for the Kepler system. So, and by the Hamiltonian.
Almost not called that.
So, are there any questions?
No, the first term is the unit vector, not the Q.
Okay, so it's generated by 7 generators, and there are 2 extra relations. So with these defining relations, and the 2 extra relations. So the sorry, what is the question?
I think maybe there's a mistake in one of the points, and when you give the wrong lens vector.
Oh, that's quite possible. Please don't pay attention to pluses, minuses. I think I didn't divide by Q somewhere.
Yeah, he wrote the angular momentum. It's not that correct. Yes.
Yeah.
Did I lose Q?
Something like that.
Anyway, the correct formula is a homework for everyone who didn't do this. So, okay. So now the spectrum of H, you will know that it's discrete. This piece is singular. That's the accumulation point of discrete spectrum. And then there is a continuum spectrum. So now let's look at the multiplicities. So the eigen subspaces of H are exactly those things that should be irreducible representations of this Fock-Pauli algebra. So for the discrete spectrum, the eigenspaces are isomorphic to Cn tensor Cn, and it's an irreducible J module because in this case it's the SO4 that acts in this tensor product, And if you just reduce it to the action of SO3, so then you will get this decomposition with the so-called azimuthal quantum numbers and so on. So then for the zero energy level, it's also an irreducible J module, which is module over E3 over the Lie algebra of three-dimensional Euclidean motions. And then same goes to the positive spectrum. So from this example, you can see the characteristic feature of quantum superintegrable systems. So the dimensions of the eigensubspaces, they can be quite large because n here can go to infinity. So and in the semi-classical limit, when h goes to 0, if we keep n of the order 1 over h, it means that our energy levels as h goes to 0, they remain finite. In this limit, the dimensions of eigensubspaces will behave like h to the minus 2. They will go to infinity. But this is a nice number because 2 in this case it's 1/2 of the dimension of the corresponding symplectic leaf in the Kepler system. Kepler system is a classical superintegrable system, and that's a typical behavior for the spaces of geometric quantization when you have here h to the minus 1/2 of the dimension of the corresponding symplectic leaf. So again, that's the key difference with quantum Liouville integrable systems. Multiplicities in quantum Liouville integrable systems are stable as h goes to 0, and multiplicities in superintegrable systems, they always have this behavior because of these extra cyclic variables. And again, one can look at the notion of quantum refinement, because here in this example, because there is a quantum superintegrable, quantum Liouville integrable system as well, with quantum integrals h, the third component of the momentum and of the length vector. So anyway, so this was a brief detour into history of science, basically, because we all learned this example of superintegrability in high school. So now, are there any questions? I don't understand. Hello?
No, it's okay. Sorry.
Okay. So now let me go to the main subject of this talk. So it's a periodic n-spin Calogero-Moser chain, you can say. So this is a joint work with Jesper Stockman. So here G is simple, compact, simply connected Lie group, and so we do the following. So let's take G to the n. It acts on itself in this particular way. So you can think of this as the following. You have a connection on a circle with n marked points, and then this connection has holonomies along these intervals. So if you just consider, if you just reduce the information about the holonomy, about the connection to the information about these holonomies, then the gauge group will be reduced to G to the n, to this gauge group located at the points, at the endpoints of these intervals. And then this gauge group will act on the holonomies exactly in this particular way. So in some sense, we have two spaces G to the n. One is connections, and the other is gauge group. So if you don't want to have this analogy with the gauge group, then it's just the following. You have the right action of g to the n on g to the n. You have the left action of g to the n to g to the n, but this left action is twisted by the translation operator. So you can think of this as a kind of twisted conjugation action. Okay, so for the Lie algebra of our group, we have a natural quantum moment map that is just because the Lie group acts on this space g to the n. We have a Lie algebra homomorphism from the Lie algebra of our Lie group to the algebra of vector fields on g to the n. So here, mu left, mu right are corresponding moment maps for the left and right multiplication, and T is the cyclic shift, the one that I already mentioned. And then all these moment maps, the left moment map, the right moment map, the moment map for the gauge action, the quantum moment maps, they lift to the homomorphism from the so this is the homomorphism of Lie algebras, and it lifts to the homomorphism of associative algebras from the universal developing algebra to the power n to the algebra of differential operators on g to the n. Okay, so once we have this gauge action, we have these three quantum moment maps, three homomorphisms. That gives two natural embeddings. One is we can take the tensor product of this universal developing algebras and then we can, using this left and right moment map, we can embed them to the differential operators on g to the n. We can also embed this universal developing algebra of our gauge algebra using the diagonal gauge moment map to the differential operators. It just happens that we can take this tensor product over the center of these algebras. The embedding still works. And then naturally in this tensor product, we can embed an individual copy of this universal developing algebra, say using left or right embedding. So we have this chain of embeddings. And then we can take Gn invariant part, and we will have the following. So Gn invariant part of this copy of the universal developing algebra is z to the n. Z is the center of the universal developing algebra. So here we'll have some interesting algebra. On the right, we will have again the center to the power n embedded into this associative algebra, and that's the structure that we have. Differential operators on g to the n, this strange associative subalgebra. In this associative subalgebra, we have the commutative subalgebra. And then what can we do with this? I'll tell you what we can we do with this. But why this is all happening? Of course, you have natural question. What does it all mean? So it's difficult to explain the true meaning of this using Lie algebras and universal developing algebras. The true meaning of this is much clear if you use the modular space of flat connections on a surface and its quantized version. So then all these constructions will be very natural, but this would take longer. I don't think I would be able to explain it the right time. So, okay, so now what we do is we want to have a quantum integrable, superintegrable system. So let's evaluate this z to the n on This is central character of this tensor product to evaluate this center to using these weights. As a result, instead of differential G invariant, differential gauge invariant differential operators, we will have this algebra. It's the differential operators on G to the n, tensor product with the endomorphisms of our finite dimensional irreducible representations, and then we take Gn invariant part. So Gn invariant parts in the appropriate sense. So then we have now we are very close to superintegrability. So now we have these subalgebras. So we have the big algebra A mu. Mu is for these central characters. So then we have an intermediate subalgebra. Again, it's determined by these central characters, and then we have a commutative subalgebra in it. So this is exactly the commutative subalgebra. As we will see, it's centralizer and the big algebra A. So you may ask, if A is a quantization of something, the answer is yes. A mu quantizes symplectic leaf that depends on n coadjoint orbits in T star G to the n over G to the n. And this symplectic leaf is obtained by the standard Hamiltonian reduction procedure. So this fits exactly into what I defined before. So now claim this is a superintegrable system. In other words, the centralizer of this commutative subalgebra in our algebra A mu is maximal. So that's in the forthcoming paper with Jesper Stockman. So now choose a representation space of A mu. So it will be the space of functions on G to the n with values in this tensor product. This talk is conceptually absolutely correct, but some details can be wrong. Okay, so it's this. We are mapping it to the zero weight subspace. So the invariance means the gauge invariance of this kind. So if you apply the gauge transformation to the argument, the gauge transformation will come out to acting on these representation spaces, and then the function itself. And then as a consequence of this, if you evaluate this function on such elements, one everywhere and Cartan in one place, then it will be in the zero weight subspace of the tensor product. Okay, claim that this is actually simple superintegrable system. In other words, the spectral subspaces are irreducible representations of this centralizer. Okay, so now something that's can be called gauge fixing. It's easy to check that for any element G in G to the n, there exists H such that H acting on G gives this combination. You take the monodromy, kind of the full holonomy from point I to point I along the circle. So remember that we have circle with points 1 to I. So you take full holonomy along the circle. It's this holonomy. And then this piece of gauge group, it acts by conjugations on this holonomy. So as a consequence of this fact, we have n capital isomorphisms. So there are n ways to identify G to the N over G to the N with G mod G, which is H mod W. So corollary of this is that our space of where the algebra acts, remember that's this space. It's actually, it should be the equality. It's this space. It can be now written as the space of functions on H with values in this zero-weight subspace of the tensor product, and the functions should be W invariant. It's nice because W acts here, and while group doesn't act on irreducible representations or on representations on finite dimensional representations of G, but it acts on zero-weight subspaces. So it's natural completion. So this is L2 space. So by C I meant, well, okay. By C I meant algebraic functions, matrix elements of irreducible representation. So it has a natural L2 completion. So this is the our big Hilbert space, and we have commuting Hamiltonians that are coming from this subalgebra. So naturally, this subalgebra, there is a simple fact that the center Zj is generated by homogeneous Casimers. Here, di's are exponents of the algebra G. So with d1 is always equal to 2, H2 is the Casimir C2. So you have all these Casimers. Letter K indicates in which part of the tensor product it's sitting. So and the nice fact is that so now all these Hamiltonians, they act on this space, and we can compute their action. These are differential operators, but there is a nice formula for quadratic Hamiltonians. Others are kind of more difficult to write, and maybe it's not necessary. So for the quadratic Hamiltonians, it can be done in the following way. Let's choose a basis in the Lie algebra, some orthonormal basis in the Cartan, root basis in G, and if there is a superindex K, that means the corresponding elements of the Kth factor in the tensor power of UG. And then there is a simple description of the quadratic Hamiltonian corresponding to K equals I. I is the place where we did the gauge fixing. The explicit formula will depend on this I, but everything is cyclically invariant, so it effectively doesn't depend. And then there is a nice formula for the difference of K plus first and Kth Hamiltonian. And that's exactly the Knyazhnik-Zamolodchikov-Bernard kind of differential operator, topological part. Here R are constant dynamical R matrices. So these are called Felder dynamical R matrices. And now the spectrum. The eigenfunctions of our Hamiltonian are given by Hamiltonians given by so-called trace functions. You choose representations with highest weights, integral dominant highest weights lambda I, and choose the intertwiners like this, and then you define the function on G to the N using the representations, intertwiners, representations, intertwiners. You go around the circle and construct this function. And after gauge fixing, there are functions on H, and these are exactly the trace functions that were considered in this. So then it's absolutely obvious from this formula that Hamiltonians act by Casimers, because this is an irreducible representation. If you take any central element, acting as a differential operator on this function on G, it gives the value of this Casimir on lambda. So this is absolutely immediate. And then this is less obvious, but this is true. The orthogonality. And then we have the decomposition of our space, big Hilbert space, into the joint eigensubspaces of the Hamiltonians. And these joint eigensubspaces are isomorphic to the tensor product of Hom spaces. I'm running out of time. Sorry about this. At the most interesting place. So then this is the way how graphically can be trace functions can be written, and then let's look at the propagator. So what is the propagator? We have n times rank Poisson commuting, not Poisson commuting differential operators. So we choose Euclidean time for each of these operators. Then these are the operators acting on our Hilbert space, and we treat them as integral operators. And then it turns out that there is this nice integral representation for the kernel of the integral operator, where these individual factors are partition functions for the two-dimensional QCD, kind of multi-Casimir two-dimensional QCD. Graphically, multi-time partition function for two-dimensional QCD on a disk, which is drawn here. G is the holonomy around the boundary of the disk. T is the parameter that is assigned to the disk. Usually, in the two-dimensional QCD, all times are 0 except for the first time that corresponds to the Casimir, and this first time is interpreted as the area of the disk. So graphically, it means the following: that so we have this circle that I started with. So now we multiply it by the time interval, and then the way how you should think about this formula is that there is this Wilson line that goes from left to right, and to each of these representation V mu that define the spin structure, kind of spins for Calogero-Moser system, you assign the Wilson line, and then you take the partition function for the disk, and you integrate over the holonomies over the edges inside, as usual in QCD. So this is basically Nicolai, Witten. So, and then there was a big industry about this. So so these are the and then the semi-group property of the propagator is just this gluing property for the cylinders. And then more generally, if you have a surface with some complicated graph in it that goes to the boundary, then you can define the partition function in the same way. And then you will see immediately that this partition function is a special solution to the Calogero-Moser spin chain dynamics. This is very similar to the fact that when you have quantum Chern-Simons, this invariance of three manifolds, if you put a conformal field theory on the boundary, then you can think of the invariance of links as special solutions to Knyazhnik-Zamolodchikov equation. So this is instead of Knyazhnik-Zamolodchikov equation. Okay, so now there are beautiful connections to Chern-Simons TQFT. That is a long story. So first steps are done in this paper. The second part should come out soon. The story about modular spaces is in this paper with Semyon Artamonov. There is a nice non-compact story that is closely related to so-called open-closed surfaces. Again, this is the forthcoming paper. That's basically when you have something like this. So G halonym is everywhere here and K halonym is everywhere here, where GK is a symmetric pair. And then there is an affine story that, okay, sorry for going over time. John, happy birthday.
Thank you, Nicolai. Sorry, I realize only now that I put the talk, it's your midnight now. I thought I miscalculated the time zone. So are there any questions?
Hello, Kolya. I would like to ask two questions. One is, of course, Vinterni's name was mentioned. So whether in the quantum superintegrable systems which they constructed, I don't know whether they are simple in your sense, or is this known that many? It seems a natural notion that the joint eigensubspace of the commuting Hamiltonians is some irreducible representation of the conserved quantities. So is this studied in the Vinterni school? I am not sure.
Sorry, I got disconnected.
Oh, you got disconnected briefly. Okay, sorry. I guess you have to.
This is the correct way to say.
At what point of the question you get disconnected? Did you hear the question?
No.
No. Okay. I guess
So am I?
can you got disconnected? So you can, yeah. You can.
Can you repeat it, please?
So can you hear it now?
Yes.
So the question is, I mean, about this notion of superintegrable system being simple. I wonder whether you mentioned the work of Vinterni, so they studied lots of quantum superintegrable systems, and
yes.
Are they simple or what is known about this?
I don't know. Actually, this is part of my homework, is to look at the this superintegrable systems that Pavel was constructing with his collaborators, and just to see what kind of representation theory is in there. But you know, this is one of the homeworks that I have, and that not completed.
So the other question is, I mean, in this spin Calogero-Moser spin chain, you focus on the quantum version, but there's a classical version of that.
Yes.
And I wonder whether it's possible to have some kind of Ruizenaz analog of this. So you start with lots of cotangent bundles for lots of copies of the group, whether to replace them by Heisenberg double and do something similar. Do you think that's possible, or this is the second question?
Yes, of course it's possible. But a better way to do it is to pass from the cotangent bundles to modular spaces. So so this particular case, T star G to the N, is related. I mean, you can do kind of relativistic nonlinear deformation, and it will be superintegrable systems on the modular space of flat connections.
Yeah, I do. Yes.
With N punctures.
Yeah, I do understand the moduli space is more general, contains more possibilities.
No. What I'm saying is that this duality with Ruizenars, then it's very natural. It's the action of the mapping class group that brings cycles corresponding to Calogero-Moser to cycles corresponding to Ruizenars. And then once you linearize the modular space along part of the cycles, then this becomes more complicated.
But is it right that this question has not been studied yet? These Ruizenaz analogous these systems.
For these systems, I mean, it was not written anywhere. That I'm almost certain. For the case n equals 1, that's in my paper from 2003. I don't remember, something like this.
Okay, I understand. Thank you very much.
Oh, no. I made the wrong. For orbits of rank 1, something like this can be done by Arutyunov and Feyron and Chalich.
Yes, I know those papers. Yes.
If it hasn't been done there, then it hasn't been done.
Okay. Okay. Thank you.
Right. So any question, John? Yeah.
Hi, Kolya. It's John here. We're running out of time, so I don't want to give a lengthy question, but it's the qualitative property, I mean, of superintegrable systems or ordinary Liouville integrable systems that I would like you to comment on. I mean, one has classical, one has quantum. Of course, the classical is essentially the foliation by tori. If you're in a compact space, that's the action angle variables. That is what prevents the system from acting generically and spreading out. But quantum mechanically, it's not quite clear what characterizes the eigenfunctions of a completely integrable Liouville integrable system. But there's just one thing that was done with which I think may be related to this question for superintegrable systems, but maybe I'm wrong. It was done some years ago by Chris Soggy and I think Steve Zeldich. And they were studying classical and quantum systems, which were essentially geodesic motion on Riemannian, on compact Riemannian manifolds, and versus the structure of the eigenfunction. So the phenomenon that they were looking at was, and this is why it's related, I think, to superintegrability, is they were looking at such geodesic flow, which in which, when you look at the space of geodesics, and you put a measure on that, then those which are closed, so one-dimensional, form a set of non-zero measure. There's some non-zero probability that the geodesics you choose are actually closed. And they showed that this property, a classical property, for the corresponding Laplacian equation, reflected itself in a property of localization. So it was, there are these bounds about how localized the wave function can be, how high up it is if it's narrow, and so on. And as you go asymptotically to larger and larger eigenvalues, they showed that these properties, that the non-zero measure on the space of closed geodesics, and the fact that you saturate the bounds that exist a priori for the degree of localization of the quantum wave function were in fact equivalent. And that sounds like it might be along the lines of a qualitative characterization of a superintegrable system because of the closed trajectories. What do you think about that? Or do you know about that?
Well, I will be reading these papers tomorrow. but let me ask you, in the classical case, in these systems, is it true that every trajectory goes along certain tori, certain torus, and there is a bound for the dimension of this tori?
Well, it's stronger. It's circles. It's closed trajectories.
So almost every trajectory is periodic.
Not almost every. A non-zero measure. So if there's 100%, but maybe 20% of them.
Maybe this is not enough. Most likely, this is some kind of KAM perturbation of a superintegrable system.
Sounds
similar. Sorry, in the Kepler, if you just go back to the Kepler problem, the Kepler problem is of course.
Yes, but what I mean is that it's a part of the phase space when the trajectories are closed. It is non-zero measure, and it's super integral.
In fact, the systems will also scattering and so on, but and collapsing. But yeah, okay. So maybe it's just in some open region, invariant region,
Okay, so any other question? If not, next time speaker.
Thank you. And John, again,
Thank
all the best.